Section 4.7 Newton's method. Suppose that a car dealer offers to sell you a car for $18,000 or for payments of $375 per month for 5 years. You would like to know what monthly interest rate the dealer is, in effect, charging you. To find the answer, you have to solve the equation 48x times 1 plus x to the 60th power minus 1 plus x to the 60th power plus 1 is equal to 0. Now, how would you solve such an equation? Now, for a quadratic equation, ax squared plus bx plus c equals 0, there is a well-known formula for the roots. For the third and fourth degree equations, there are also formulas for the roots, but they are extremely complicated. If the function f is a polynomial of degree 5 or higher, there is no such formula. Likewise, there is no formula that will enable us to find the exact roots of a transcendental equation, such as cosine of x is equal to x. We can find an approximate solution to equation 1 by plotting the left side of the equation using a graphing device, and after experimenting with viewing rectangles, we produce the graph in figure 1 below here. So here's our graph. Now, we see that in addition to the solution where x is equal to 0, which doesn't interest us, there is a solution that's between 0.007 and 0.008. Zooming in shows that the root is approximately 0.0076. If we need more accuracy, we could zoom in repeatedly, but that becomes tiresome. A faster alternative is to use a numerical root finder on a calculator or computer algebra system. If we do so, we find that root, correct to 9 decimal places, which is 0.007628603. Now, how do those numerical root finders work? Well, they use a variety of methods, but most of them make some use of Newton's method, also called Newton-Raphson's method. We've explained how this method works, partly to show what happens inside a calculator or computer, and partly as an application of the idea of linear approximation. The geometry behind Newton's method is shown here below, where the root that we are trying to find is labeled r. So here, if you take a look here, we have this curve. We want to find this root r. L represents the tangent line to that curve. The function is y is equal to f of x. Okay, and then we have this x1, and this x1 has an output of f of x1. And then if you can see here, this tangent line goes to the point of x2. So what we do is we start with a first approximation x1, which is obtained by guessing, or from a rough sketch of the graph of the function f, or from a computer-generated graph of f. Now consider the tangent line L to the curve y is equal to f of x, and at the point x1, f of x1, and look at the x-intercept of L. Well, that x-intercept is labeled as x2. The idea behind Newton's method is that the tangent line is close to the curve, and so its x-intercept, x2, is close to the x-intercept of the curve, namely the root r that we are seeking. Because the tangent is a line, we can easily find its x-intercept. To find a formula for x2 in terms of x1, we use the fact that the slope of L is f prime of x1. So its equation is the following: y minus f of x1 is equal to f prime of x1 times x minus x1. And now, since the x-intercept of L is going to be x2, we set y equal to 0. So that means that we know that this y is going to equal 0. So if we let y equal 0, so that y becomes 0. And then we also let, since we know the x-intercept, x2, so x2 is going to become the following for the x value. So now what we can do is we can solve f prime of x1, we can solve this equation for x2. So what we're going to do is we divide both sides by f prime of x1, and then we add x1 to both sides. So therefore x2 is going to equal x1 minus f of x1 divided by f prime of x1. Now, we use x2 as a second approximation to r. Next, we repeat this procedure with x1 replaced by the second approximation x2 using the tangent line at x2 f of x2. So what we're doing is now, okay, we technically are going to have another line, and let me draw that line here. That starts here at x2. Okay, and then that line is going to hit the curve, and then we're going to have another tangent line. So we'll see that in the next figure. So this gives us a third approximation. Okay, so now we have x subscript 3, which now x1 is replaced with x2 minus f of x2 over f prime of x2. And if we keep repeating this process, we obtain a sequence of approximations, x subscript 1 all the way to x subscript 4, as shown here in this figure. So you can see here, now that we draw that line, now we create another tangent line, which is x3. We create another line, which is x4, which is getting closer and closer to that value of r. So in general, if the nth approximation is x subscript n and f prime of x subscript n, then the next approximation is given by the following. So x subscript n plus 1 is equal to x subscript n minus f of x subscript n divided by f prime of x subscript n. Now, if the numbers x subscript n becomes closer and closer to r as n becomes large, then we say that the sequence converges to r, and we write this as the limit as n approaches infinity of x subscript n is equal to r. Now, although the sequence of successive approximation converges to the desired root for functions of the type that was illustrated in Figure 3, in certain circumstances the sequence may not converge. So for example, let's consider the situation that's shown below. So here we have this graph, right? There is r, there's x1, there's x2, and there's x3. You can see that x2 is a worse approximation than x subscript 1. This is likely to be the case when the derivative of x subscript 1 is close to 0. It might even happen that an approximation, such as x subscript 3 here, falls outside of the domain of that function. Then Newton's method fails, and a better initial approximation, x subscript 1, should be chosen. Now, there are specific examples in the homework in which Newton's method works very slowly or does not work at